Okay, cool.
Go, Dad.
Let's get started. Okay, guys, thank you for coming. All right, so I was talking to my good friend Mike. Let's just actually start playing this. And he wanted to set up a mailbox. In other words, not just an email mailbox, but he wanted to basically set up some sort of device where we can put something in his mailbox, and essentially it would indicate to him when a mail has arrived. So a literal mailbox. Yeah. But when we're actually doing this, there are certain constraints we need to consider, right? How do we trigger the mail event? So in other words, how do we know when something's opened or closed or whatever? What are some of the constraints that we have? Okay, and one of the biggest constraints that we're actually talking about is essentially power. I've got a box of tricks over here. Yes, that's a box of tricks. Okay. I'm pretty sure most of you have seen these sort of gadgets before, but essentially this is the question, might answer the question as to how do I basically trigger a mailbox? So that's a reed switch. You basically hold that next to a magnet, it'll basically close a switch, and you basically open it, and it's basically you take the magnet away and it closes again. So that's essentially a closed switch. I'm sure you've all seen reed switches. What about a tilt sensor? You can put this on the flap, right, or essentially the door. So as basically the door opens or closes, then essentially you can see how that works. There's a piece of mercury inside there, and it basically opens and closes. Okay. So if you're looking at something like a reed switch with a magnet, or you're looking at something like a tilt switch, you need some sort of mechanical interface. You know, either essentially the letterbox needs to essentially have a flap, or you need to basically open up a door. Okay. Some of these mailboxes don't have these sort of things, and then you don't have an option for actually going with the physical switch. You've got to do something like this, which is essentially an IR sensor. So you have an IR LED, an infrared LED, and an infrared sensor. Okay, and you basically got to have the ones, like going from the bottom of the mailbox and then from the top of the mailbox, and then essentially when mail goes in, it'll break that beam. But so we can basically figure out ways to basically trigger an event when mail arrives. Okay. The issue is, right, that if we basically were to actually run it on a battery, okay, we would very quickly run out of that battery. Now, if we have a look at this website over here. Let's see, where did that open up? There we go. So this is essentially a list of batteries, if you have a look on the line, right? So these are all the various different types of batteries that you could get. And the things that are important, right, are essentially, there's two columns that you could pay attention to. The first one is essentially the voltage, and the second one is this milliamp hours, okay? So the voltage basically tells you how much essentially potential current or potential difference it's got, but and how much voltage it can generate. And milliamp hours is the capacity as to how much it can actually store. Okay. Now, the ESP32s, right, that we basically have over here, they run on 3.2 volts. Okay. So if you have a look at a lot of these particular batteries, like if we have a look at, let's say, for example, the triple A's or the double A's, they all basically have a voltage of 1.5 volts, or anywhere between, let's say, 1.2 volts and 1.5 volts. So they're not powerful enough in terms of voltage to power up these devices. It is possible to basically boost that voltage using something called a boost converter, but when you do that, you pay in the capacity. So if you want to basically take a 1.5 volts and boost it up to 3.3 volts, you're going to basically sacrifice some of the capacity that you've got. Okay. Now, I have here. I'm just going to basically show you. You've seen all these batteries before, and it'd be interesting to basically have a look at how much they have. Like, double A's is essentially 1,200 milliamp hours. This double A's got a 2,700, which is excessively good, and so on and so forth. And it goes down and down. Look at this guy. This is an 8,000 milliamp hour. That's crazy big. Okay. In most projects that we use, we use either the little sort of square batteries, or we use something like this. Okay. So this over here, let's just undo this. That's a 3,400 milliamp hour battery. What's the name of this battery called again? This is a 18650. That's right. Okay. And there's certain things that we need to talk about when actually using these sort of batteries as well. So I have over here a little basically project which I'm going to share with you guys. Okay, on GitHub. And effectively what happens is if you start looking at this, it goes through a bunch of different tests or a bunch of different things, and I'll basically walk through what these are. The first thing I want to do is just to basically say, all right, let's go ahead and get benchmark online. Okay, and I'll just very quickly show you this code. I'm not going to go too deep into it because this is, effectively a piece of code that's basically going to the internet, and it's looking for this particular file over here. Okay, and that particular file is actually War and Peace. So it's one of the largest books, or a huge novel. It's a text file, and it's several hundred megabytes large. It's like crazy big. Okay. So what I'm going to do is I'm just going to basically switch over here. Okay, so you're looking at what you're looking at here is you're looking at the voltage as well as the milliamps that are basically being fed off the battery. So I'll see if I can zoom in just a little bit. Okay, so you can see that it's not consuming a heck of a lot of power at this point in time. Okay, let's go ahead and try and flash it with this particular. And I hope I wired it up correctly, because it does have different options to wire it up. It gets a little confusing, but let's have a look and see what actually we can see. So I'll go back to my camera. Okay. All right. And you can see over here that it's basically just flashing that chip. You can see that that's come up to about 39 milliamps. Okay, so the Wi-Fi is connecting. It's now basically got its connection. It's got an IP address, and now it's actually starting to download. And you can see it's actually downloading in chunks. Okay, but this is not actually getting the right value. So I think I basically plugged this in incorrectly. Let me just change this quickly. 1 second, which is a bit weird. Oh, there it is. Yeah. Okay. Cool. All right. So if we have a look at that. You can see that it's basically ranging anywhere between essentially 100 milliamps and 30 milliamps as it's basically getting its chunks. And there's actually a very cool little sort of feature on here, if I can see if I can find it for you. Let's see if we can. Ah, there we go. Right. Okay, cool. So you can see it's basically going to roughly 140, almost 450 milliamps in it, but so effectively it's drawing a tremendous amount of power as it's basically going through. Okay. Now, if we basically take one of these batteries that we were looking at earlier on, okay, and let's just basically average it out to 100 milliamps while it's basically online. And this is actually just receiving, it's not even transmitting. Okay, so if we take one of these particular batteries, let's go for one of these guys. Okay, this is a very good nickel cadmium at AA at 2,700 milliamp hours. So if we basically take a calculator and we go 2,700 divided by 100, okay, that gives you the time. All right, as to how long, how many hours it's going to actually last. So after just over a day, this battery is going to go run flat. If I basically ran this program on one of those batteries, and that's not really the whole story, because the truth of the matter is that that's a 1.5 volt battery. Remember that I said that if I wanted to actually boost it up to 3.3 volts, I'd have to basically sacrifice more of that cost. And there are calculations or calculators out there that will help you actually calculate what that cost is. So generally what you would do is you basically have like 2 or 3 batteries, and then instead of actually boosting it up, you would basically buck it down, okay? All right. So that basically gives you an idea as to how long a battery like that would last. So if we basically got our post box and we basically had a full-time internet and full-time connection, you'd have to change the battery once a day, which is just not feasible. Okay, so that's essentially the story over that. Okay, let's go back to the slides. Okay, so you could basically hunt around for various different batteries, and you could have a look at the, how much capacity. The more, the better. Okay, but still, you'll need to come up with a better solution. And one of the best solutions that you could come up with is the fact that you can then sleep the actual ESP32. Okay, and what that basically means is that we can basically reduce the amount of power consumption when we're actually not needing it, and we can extend the battery life. And as you'll see, it basically goes from 1 day, and we can all of a sudden get more than a year out of it. Now, the ESP32 has got various different modes of sleep. It's got modem sleep, which is effectively just powering down the modem while the chip is running, which, because as you can see now, it was ranging between 100 and 150 milliamps. Sometimes it's got these very, very sharp spikes in it. If you could basically just sleep the modem and then essentially just wake up, get a packet, and then turn the modem back to sleep, you could effectively save power like that. Then we've got 3 other different sleep modes, and we'll go into these in detail. Light sleep, deep sleep, and then essentially hibernate. Okay. All right. So this is effectively from the datasheet. Okay, and we'll have a look at that also on this little sort of spectrum as we go through. When we basically are having when we have the radio working on the ESP32, right, and it's basically transmitting, we can basically see that we can get anywhere between 160 and 260 milliamps of usage. Now that doesn't mean that it's continuous; it's spiky, okay, but still that's something that you need to keep in mind, okay. And we have the capability of affecting the amount of dBm on the actual device. So we could turn up how much power the radio is transmitting, and obviously the more power it has, the higher amount of milliamps it's going to consume. If we basically set it to 0 dBm, it's going to be at about 120 milliamps. Okay, again that's spiky, but it's something to keep in mind. Okay. Now if we're that's TX, right? So both of these things are transmitting. If we're just listening, we're looking at between 80 and 90 milliamps, which is not too bad. Okay. Now, when we say that we're basically just listening, what we're talking about there is somebody sitting in a lab with one of these Wi-Fis and putting effectively binary, or basically just raw data over the network, trying to actually figure out how much data that is. When we're actually doing this in real life, okay, it's different, because when we're doing it in real life, we're basically looking at a TCP/IP stack, we're looking at an HTTP stack on top of it. There's lots of basically going backwards and forwards, there's lots of communication. So these values will change and be different depending on how things work in real life, okay? Just by the way, just out of interest sakes, if you have a look at what that was actually transmitting earlier on, I just want to show you that quickly, because this is also quite interesting. All right, you can see over here, the actual millibytes per second. You can see it's essentially 0.13.
Megabytes per second.
It's not megabytes, megabits per second. Okay, and that's very slow. Now I actually can ramp this up. It depends on the network. It depends on the speed. It depends on many other things. This was a big sort of thing that I actually had with guys that I was working with. They basically read the data sheets of the ESP32, and they basically misread 20 megabits per second, right, to 20 megabytes per second. And I'm like, dude, there is no ways in hell you're going to get 20 megabytes per second, and I'm very unlikely you're going to get 20 megabits per second. That's ideal conditions, okay? That's raw data, that's with no TCP/IP stack, and that's essentially in a Faraday cage. I can basically push that up to 6 megabits per second if I increase the speed, if I basically give the Wi-Fi more memory. But what you see in the data sheets, you've got to realize that they're basically doing that in a perfect condition in a lab. This is essentially what you could typically expect, okay? And this applies to this as well, okay? All right, so now we're talking about with no connectivity, all right? How much does it actually consume? Because maybe we don't want our post box to basically be sitting there on the radio all the time. we could effectively wait for this trigger, this event that we looked at, either with a tilt sensor or with the read switch or this IR to come in. And essentially once that's actually triggered, then we go onto the internet. So what that basically means is that we would be consuming anywhere between 20 milliamps, all right, and 3 milliamps, depending on how fast we set up our speed or how fast we set up our chip. Okay, and then essentially when we go online, we would jump up to, let's say, for example, 120 milliamps, and then jump down to 3 milliamps. Okay, now interestingly, if we basically have a look at that calculator again, okay, do you recall how much that battery was? 2,700. Yeah, 2,700. If we divide that by 3, now all of a sudden we get 900 hours. Okay, divided by 24. So instead of 1 day, we're now at almost a month, right? Just by basically saying that we're not going to basically run the radio full time. We're only going to be, doing it, when we need to. Okay. So maybe we basically switch it on once a day for 100 milliseconds. Oh, sorry, we switch it on for once a day for like a second or two, and that's going to run at 120 milliamps, and then essentially it's going to go back down to 3 milliamps. But still, a month is probably not good enough. You don't want to basically have to change a battery once a month. And this is assuming that we've got a 3.3 volt battery that's essentially got 2,700 milliamp hours, not a 1.5 milliamp battery. Okay. Now we basically come up to the sleep modes. All right. First one is light sleep. Now look how much that drops. That drops from 3 milliamps down to 0.8 milliamps. Okay, that's a significant drop. Okay. All right, and then essentially we get into deep sleep, okay? And we can now control, and I'll show you how you do this with the ESP32, you can control how much of the chip is going to be in active or basically sleeping. And it can range between 0.15 milliamps, okay, that's 115 microamps, all the way down to 2.5 microamps, okay? Now, if we were to run that on a battery, let's just take that same thing again. So if we had a 2,700 milliamp hour battery, and we divided that by 0.12345 that would last that many hours. Okay, it's just ridiculous. Okay, that's several years. Okay, of battery power. All right, good. So let's go on to the next slide. Any questions so far? Everybody happy? Okay. I hope it's interesting. All right. So effectively, right, when you actually are going into the various different sleep modes, right, you can basically control what you want to actually switch off. With light sleep, right, we can switch off the peripherals. We switch off Bluetooth. We switch off Wi-Fi. Now the cores are actually still running with light sleep. Now on the ESP32, in case you didn't know, right, we've got 2 cores, okay? And then we've got something else called the ULP, which is essentially the ultra low processor unit, which is essentially a third CPU on the device. We've actually got 3 CPUs, okay? And with light sleep, right, we keep the cores running, the coprocessor and the CPU, okay? Now, you notice that the peripherals are switched off here, but it's not quite all true, because when we talk about peripherals, what are we talking about? We're talking about things like the serial buses, the I2C. How do I communicate to various different things, such as tilt sensors or temperature sensors or what it is, right? Peripherals such as SPI, maybe I've got a screen display or something like that, okay? What's really interesting is that when we say the peripherals are off, we say that the core peripherals are off, all right? The coprocessor has got its own I2C bus. And you can actually use that in both sleep and deep sleep. Okay? The only problem is, right, that the coprocessor, you don't program in C, you program that in assembler. So it's a little bit tougher. Okay? But nonetheless, it is possible. Okay. All right, so those are the various different things. Now, with deep sleep, right, as you'll see, we basically can control how much of that of the actual device we want to shut down. Okay. Right, and then we come across this thing over here, RTC. I want to talk about that for a moment. This is essentially an integral part of the chip, real-time clock, okay? We all heard about the chips that need a real-time clock. Every computer has got a little real-time clock in it. It's a little circuit that you basically plug into it, and it keeps things like your time on your CPU, or on your computer. So, like if your battery runs down on your phone and your phone switches off, there's a secondary battery that powers up this RTC that will basically mean when you switch it on, you haven't lost time. It essentially keeps track of time. It's one of the problems that we have at our work with the Raspberry Pi. The Raspberry Pi doesn't have an RTC. It doesn't have an external battery or whatever. Now, in the ESP32, we have an RTC. It doesn't work as the same as it doesn't have an external battery, but it works just the same as an RTC. It keeps its time, it keeps sync, it keeps remembrance of what's going on inside the chip. Okay, and you'll see that actually is an integral part of how things work. Okay, so these are the various different wake-up modes. Okay, so when we basically have gone to sleep, all right, we can wake up either with a timer, we can wake up with a touchpad, or we can wake up with an external pull-up or pull-down resistor. In other words, we can wake up with a button switch, and we'll have a look at that in just a moment. And essentially, with as I mentioned, right, with the ultra-low processing unit, if you know how to program an assembler, you can also wake up the chip using A to D conversion. So you can basically measure a voltage and wake it up with that. And then you can also wake it up with I2C. So if we basically go back a couple of slides, if we were doing that, okay, you can imagine, right, that essentially we would be running something like 0.15 milliamps, okay, and then essentially we wake it up. Then we basically wake up to something like this 20 milliamps over here, or 3 milliamps, depending on how much speed we've got. Then we go online, and we basically then consume, let's say, 120 milliamps. Then we go offline, and then essentially we're consuming 3 milliamps, and then we shut it down, and then we back down to essentially these sort of units over here. And we can actually have that still running with an I2C trigger, or with an A to D trigger, with so you can measure a temperature, or you've got and you can switch it on with a temperature or something like that. Yeah.
What's I2C?
I2C is essentially a bus system that basically allows you to communicate. Think of like if we have USB or serial communications. So I2C is essentially a 2-wire communication system. And if I show you these guys, here we are. Okay, so if I show you these guys, so you need, just think about this, right? So you need power, and you need 2 wires, okay? And with those, you can basically talk to these devices. This is a tilt sensor, so this is an accelerometer, like you have on your phone. So this will basically give you, right, how things are tilting in terms of XY coordinates. This is a temperature sensor, also I2C. This is a humidity and pressure sensor, I2C. All right, I2C and SPI are 2 buses that are common. SPI basically SPI uses 4 wires, I2C uses 2 wires, and you can drive just about anything with them, from displays to temperature sensors to everything. Okay.
Is this SPY?
No, that's just that's not a SPI. That's actually just normal touch. That's actually just a close and open circuit.
Okay.
Okay. Most of these things over here are actually just open and closed circuits. I don't have any screens or anything else like that. But touch screens and all that sort of stuff, those are usually SPI. Okay. All right.
Does the ADC run at full speed, or is it?
No, it wouldn't be. It'll be basically running at slow speed here.
So really slow, or just moderately slow?
So there's actually 2 different. So when we're talking about the RTC, we'll go into this in just a moment. The RTC basically has 2 different clock speeds, a fast speed and a slow speed. So your general chip operates off the RTC fast speed, but when it goes to sleep, right, it can operate off the slow speed. But you can actually configure it to basically remain on. Obviously, you get charged in terms of power usage. So if you keep the fast RTC on, then you basically are going to consume more memory. Okay.
So when the slow RTC is running, that's waking up to do an ADC conversion.
It'll actually stay asleep. So the ATD conversion will happen on the ULP, on the ultra low processing power. Okay. And then essentially the ultra low processor will give the command to the CPU to wake up. Okay. Okay. All right. So let's have a look at this. This is pretty interesting. So let's just say, right, that so this is essentially a little calculator that you get online, okay, and it does this exact same calculation that we looked at before, except for it basically takes in sleep into consideration, okay. So let's say that our code execution, all right, is going to basically run. You know, how long does it take to actually measure either a very light switch, or essentially if we're doing a timer, maybe we've got an infrared beam that's looking for the thing, and we basically want to do that once or twice a day. All right, how long does it take to actually run that? Probably about 100 milliseconds. Let's be really generous and say a second, because we want also time to basically connect to the internet and basically send through an MQTT message or a REST message to basically say, yeah, there's something there, or you haven't received mail or something like that. Okay.
So it would have to cater for, you know, initializing the Wi-Fi stack. And
yes.
Yeah.
That's right. So let's say once, or let's be generous, let's say 2 seconds, okay? So let's say 2 seconds, okay? Now after it's been on, how many times a day do we actually want to actually run this code? How many times do we want to check it? So let's say, for example, we want to check it 4 times a day. Well, you know, so if we basically say 4 times a day, how many times are we dividing that in a day? So we're saying, you know, every 6 hours, okay? So so the sleep time is going to be 6 hours, and then we're going to wake up for 2 seconds, okay? So 6 times 60 is 120, no? 6 hours?
3,600 times 60, yeah.
Yeah, so what is that? 3,600 times 60? 216000. Okay, so it's going to sleep for 6 hours, wake up for 2 seconds, okay? Now, our current consumption during execution. Let's be really generous here, because we're essentially, let's say we boost up the radio receiver because we're quite far away. So we'll basically say 160 milliamps, okay, which is like extreme, okay, for 2 seconds, okay?
2 seconds, you might include connecting to a Wi-Fi.
AP. Yeah. Not long enough.
All right, make it 5 seconds.
Yeah.
Okay,
5
make it 5
seconds
seconds.
probably, yeah, that would work probably.
Okay.
Wi-Fi's take forever to
Yeah, okay. All right, so 5 seconds. Okay, but remember, during its time of 5 seconds, it's not going to be consuming 160 milliamps. It's just going to basically be pulling the Wi-Fi. But let's just say that it's on full blast for. Let's say we've got an awful setup and whatever. Okay.
I think you've got an extra 0 on your sleep.
Okay. 216. Yeah, you're right. Okay, good. Thanks for catching that. Okay, consumption in sleep mode. Okay, so now we've got those various different options. Okay. We basically can have a look at this chart over here, all right? But there's a big but, okay? This is just the chip. It's not the rest of the circuit, okay? And I can't get nearly these amount of figures as you see basically on this chip. Why? Because I've got a voltage regulator. I don't have a buck converter. I've got an LED on it, okay? So, so this thing is incredibly inefficient, okay? But let's just basically just for exercise and for our purposes, let's just say that we basically are going to put this thing into a deep sleep of 0.15 milliamps. Okay. So 150 micrograms. Okay. Now our power of a battery, let's say, is we're going to keep that at 2,700. Now this is also an interesting one, right? With most of these batteries, we do not want to drain them completely. We can't consider that the full battery length is what we actually need, because it gets dangerous. They actually get destroyed.
Left on a lithium battery.
Yeah. So let's make it 20%.
Yeah.
Okay. All right. So in this particular case, it's going to last for 481 days and 7 hours. In this particular case. So we went from 1 day running full time to over a year. Okay. Okay, and that's at 2,700 milliamp hours, and that's without something like a solar cell.
Yeah, not even
Okay.
no solar as well.
Yeah. So, and you can improve that. You could drastically improve that. I mean, you know, let's say for example, you only want to check it twice a day. You've doubled the amount of time that you've actually, you know, then you're looking at 3 or 4 years.
Yeah.
Yeah.
So in our letterbox example, where you'd be triggering it via a read switch, for example.
Yeah.
So you'd be monitoring a pull-up,
Yes.
a pull-up digital input
Yes.
Gpio. You would be running in deep sleep, and you can still pick up those so you can still use these numbers.
Yes. We'll have a
And-
look at that.
Cool.
Yeah.
Sorry, I'm jumping ahead.
No, that's fine. Yeah. That's all cool. All right. We'll get into the nitty-gritties of that in just a moment. Okay. Right. Okay. Well, that's exactly where we're at the moment. Okay. So we saw what it's like basically running at full power. Okay. Let's have a look at what it looks like with light sleep, and let's actually walk through what happens with light sleep. Okay. So I'll switch over to the light sleep one. In fact, let me just go to main over here and just basically comment this guy out. And we'll basically uncomment this guy out. Okay. And I'll start to compile it, and then we'll walk through the code while it's flashing. So in order for me to basically go into light sleep, all right, I can go ESP sleep enable timer wake up. This is for timing, okay? So this is when I want to basically check it periodically. And I can basically pass it a UN64 in milliseconds, okay? So so this is 5 seconds, okay, in terms of microseconds. Okay, so that's microseconds that it's requesting us. So 5 million microseconds is 5 seconds. Okay, then it'll basically say going for that. Now, basically, what I'll do is I'll just comment this out. I'll just explain to you what this is over here. Okay, and then essentially we'll retry this. Okay. Okay, so what you'll notice if I basically comment that out. I'll just wait for it to get there. So what you'll notice is we get nothing on the output, okay? And then it goes to sleep. 5, 4, 3, 2, 1. Then it wakes up, and then it says going for the nap. So what actually happened there, right, in this particular case, is it actually started to basically send that to the serial buffer, and then it went to sleep before it had a chance to flush the serial buffer, and then it woke up, which is why we get that particular strange output, which is why we basically have over here this URTX idle wait. So this effectively waits for the serial bus to basically flush, and then it then goes to sleep after that, okay? So then essentially once we've done that, we say ESP light sleep start, and then it goes into a light sleep, okay? And that's essentially where it halts. Okay. Now this over here, this line over here, before and after, what that's basically doing is just getting the microsecond count of the amount of time that the chip was essentially on. So what we're doing is we're basically getting a snapshot of before, how many milliseconds the thing was awake before, and then we get a snapshot of how many milliseconds after, and then essentially over here we can say nap for after minus before, and that gives me microseconds, so I divide that by 1,000, and that gives me milliseconds. And I can see that it's napped for 5,000 milliseconds. Now, what's very interesting about light sleep is you notice I can basically start to put the chip in light sleep right in the middle of the code, and when it basically wakes up after its predefined time over here at the top, right, it basically continues execution. Okay? And this is one of the advantages of working with light sleep over deep sleep. Deep sleep will reset the chip. It starts from the beginning. It boots, it goes, it starts its boost sequence again. All right? So light sleep, it makes it simpler because you don't have to start the program from the beginning. Okay, you can continue from where you left off. All right? The cost of that, right, as we basically saw, is... Sorry?
More like a Hulk.
It's more like a halt. But remember that while it is a halt, it's also basically shutting down all of the peripherals it doesn't need. Okay, and it basically goes into a status of light sleep. So it's not just a halt. It's not like a delay. It's it's essentially it basically what's it called? Clocks its
But your serial buffer example before was still kept.
it kept it in the memory.
So
It's still there in the memory.
serial
But
data wasn't in the peripherals memory, it was in the main memory.
yeah, that's right. It hasn't been flushed out yet. Okay, but yeah. So effectively, all of that stuff, right? It's not like it shuts down or basically it phaseless loss. In other words, it just halts it all. It basically just freezes everything. So that's not consuming any power. And there, your cost is essentially 0.8 milliamps. Okay. Now, so that's essentially what light sleep does. It gives you that capability of halting the application, and then you can continue afterwards. And you've effectively saved quite a lot of CPU cycles, and you've saved quite a lot of power by stopping everything from going on because you don't need it at that point. Okay, and you can effectively increase that.
Something like your example before,
Yeah.
back to that again, where you wrote out to serial buffer.
Yes.
If the hardware has any buffering, what actually happens there? Does the
You got to wait for it and check for it. So you should probably you would want to you'd want to make sure that everything that you've done is flushed up into that point.
and you have to do that?
Probably, yes. Yeah.
Because that instruction was it ESP light and sleep start.
Yes.
Does that wait for that hardware buffers to flush?
No. So you want to make sure that everything is in a state where you want to basically sleep there. Yeah. Yeah. Which is one of the reasons why we go this URTX wait till to idle. That's us basically taking responsibility for it. And you could use that not only on the serial bus that we have for the monitor, but you could use that for other serial buses as well. Okay. Obviously, like for example with
It's like the UARTs often have like, even if it's 1 or 2 bytes, they have their own hardware buffer.
Yeah.
1 or 2 bytes. Because they're holding the byte while they're pumping out the bits.
that's right, yes.
So that byte,
You want to make sure that that's flushed. And you can use this command like that to make sure that it's out. With things like communications, it's a bit easier, or essentially internet communications, because effectively you're going to wait for that acknowledgement. You're going to wait for your 200, or you're going to wait for your MQTT message to basically come back with an OK response. Yeah. Okay, so that is light sleep. Okay, any questions on light sleep? Okay, very straightforward, right? It's very, very easy. If you think about it, it's actually just 3 lines of code. It's this ESP sleep enable timer wake up. It's essentially ESP light sleep start. Okay, and that's it, really. It's just those 2 lines of code, really. That's pretty much it. Okay. All right. So let's go to main, and let's look at. Oh, one thing I wanted to actually do while this thing is running, because it's actually still running in light sleep. Okay, in fact, we'll have to. Okay, let's do it this way. I'm going to increase that to from 5 seconds to 50 seconds. Okay, so that it runs for some time. And let's flash that again. And this time, just wait for it to start up. So remember, it was 0.8 milliamps, right? That we would expect from the chip. Let's see if we get anywhere close to that. I can guarantee you we won't. Okay. Now, okay, so it's going for a nap, okay. And at this point in time, it is sleeping, and it's almost at 21 milliamps. And I can tell you now that this probably is the culprit over here, this regulator. That's dispensing a lot of heat. And this LED is also basically probably about 5 milliamps or whatever. So, between those two, we're
Switchbone regulator or linear regulator?
No, this is a linear regulator. Yeah, it's just a linear regulator, and that's probably why, it's basically so expensive. Interestingly enough, if I disconnect the RX and TX, it seems to drop by about 3 milliamps. So if I basically stop this and then go back here,
How important is the regulator?
you see that it actually does drop quite significantly. So that regulator is basically taking that 5 volts and dropping it down to 3.3 volts. If it didn't do that, the trip would fry. So we need a way to basically get that 3.3 volt standard. Okay. Now, regulator is very inefficient, and there are other ways to do it, and I'll discuss those a bit later.
The chip, do you know whether the chip has much of a voltage range, or does it have to be?
It's not very high, like 3.3 to 3. I think 3.2 to 3.6 or something like that.
Yeah, you'll buy the chip above 4.5 volts or something.
Yes.
Pretty sure.
Yeah, I've bricked several chips by accidentally collecting the 5, because these dev boards have got a 5 volt pin on them, and I very often basically touch one of the other GPIOs. That's it, in the trash. Okay. Speaking of which, this is a really interesting. I just want to show this to you guys quickly. This is a really interesting battery. This is one of my favorites. Just check this guy out. This is got a AA size. Okay, so you can see this, right? It's not a very. This one is. What is this?
It's not on the camera.
Huh? Yeah. Well, it's on that camera. So let's have a look. So this is a. Okay. Let's have a look and see if. Okay. So this is a 600 milliamp hour battery. So not tremendously big. Okay. It's not huge capacity. Okay. But the beauty about this, if you have a look at this, right, this is a Life Vapor 4 battery. Okay. So these kids are relatively new on the block.
And they're safe too.
Okay, they're very safe. They don't blow up, right? What's beauty about them is they are essentially a 3.3 volt output, and they charge at linear at 3.6. So you can basically plug this directly into an ESP32 and still have its charging circuit without having any other regulators. So even though they don't have the battery capacity, for microcontrollers, they're actually very good for that. They're very clever. You know?
So it's a lithium.
Yes, a lithium polymer. Yeah. You can get higher ones. You can get up to like 800 milliamp hours and so on and so forth. Okay. But yeah, that's one of the big advantage of Life Vapor 4. Okay.
Yeah. Less density.
Yeah.
Power density, but yeah.
Okay.
Less voltage.
Right, so the next one that we wanted to have a look at is Light Sleep with Gpio. Okay, so let's have a look at that. So we'll go back to main. So this was Light Sleep with a timer. Let's have a look and see what is required for our Gpio to work. Okay, so here we go. Light Sleep Gpio. Okay, so the code is also quite simple. Okay, we select a pin, and I'm basically going to be using pin 0 at this point in time. Pin 0, by the way, is this button here. So it's one of the little onboard ones. I can't remember if it's that one or the one next to it. I'll find out. One resets it, the other one is the Gpio 0. All right, so we set the direction. We basically say Gpio wake up enable, and then we can basically set it to a low level or a high level. So we can decide whether or not we want it low or high. Okay. And then essentially we do the same thing, ESP sleep enable wake up. Now this one has also got a timer wake up, but we don't actually need that at this point in time. And then essentially what you find over here is we use this command to basically get the level. So when we say RTC GPIO, we're talking about the ULP, the ultra low power processing unit. So he's now looking at that GPIO. Okay. So that's essentially how we do that. Okay. So we say RTC GPIO get level, and essentially we wait for it to be released. All right. And once it's released, then we can basically say what that particular what actually caused it to wake up. So we can say over here, all right, was it essentially the fact that, see, we've got that RTC idle again. So once we basically say light start, because we basically set up the GPIO, we can either wake up with the time, or we can wake up with the touch, or with the switch. And over here we can basically say which reason was it for. Was it for the fact that there was a timer or a button? Okay. So over here we can see what it's been doing. It's going for a nap and then essentially waking up every 5 seconds. Now I'll try to press one of these, and that was the reset one. So going for the nap, and essentially you can see, okay, please release the button. So there, please release the button, and it woke up because it was...
Yeah, it only went for 3 seconds before wake up.
Yes.
Then, yeah.
So over here you can see 722 milliseconds, and so on.
Cool.
Okay, and if I leave it, then it'll wake up because of a timer.
You don't have to worry about debouncing or anything like that.
I'm not doing that at this point in time, but yeah, generally you would. Okay.
Probably less critical though, because you're not worried about a double, because you're just going to execute a fixed script typically.
That's right.
And so it's not going to like double execute or something. It's only when you're trying to differentiate between the buttons, long press and things like that.
It's the same thing where when you've got these, like, you know, if you've got, let's say for example, this tilt switch on your post box, right? Once you actually execute the wake up call, if that thing is bouncing, who
Yeah,
cares?
exactly. It's just ignore it. That
You
point,
know,
yeah.
If the wind's blowing and the door's moving a little bit,
Actually, that's a fair point. It's like if yeah.
and your rusty old door on your mailbox is
That's-
moving.
That's right.
Yeah, you're gonna get a lot of mail that day.
Yeah, that's right. That's right, exactly.
You get some bounce in your switch.
Didn't we say doubles as a win in the cab? That's really cool.
Yeah. So yeah, you would have to cater for stuff like that. Yeah, unless you use the timer, in which case you basically, you know, like infrared or. I was thinking of also using something like a load sensor. I'm not sure if you could get a load sensor that'd be light enough or sensitive enough, like a load cell, like a, you know.
The trick is just have a very reliable switch. Just
Yeah.
make sure it's like a, you know, reed switch or something with good movement and
Yeah.
not like hanging on the thread.
Yeah, infrared is good, but infrared can get dirty, you know.
The trouble with infrared too, like I had a laser setup, but if you read the fine print, you realise the laser has only got so many hours of life. So if you set it up for a letterbox, it'll be great for 6 months, and then like the
I'm sure you
laser's
could,
dead.
yeah, you could probably get more than that. And these infrared LEDs, they can last for years, you know.
That's true. That's probably more reliable.
Yeah, and they're probably cheaper than the lasers.
Yeah. Yeah.
Well, you could just use an RC filter with his dresses or something.
You could do that as well.
Yeah.
Yeah. In fact, the ESP32 has got a built-in hysteresis, or essentially a magnetometer built into it. If you put a magnet straight onto it, you can actually, you know, so you don't even need a separate thing.
So you wouldn't need
that
a
right?
reed switch. You could use the magnet.
You could.
That's really interesting. That's a minimalist solution.
Although I don't know if that would work with deep sleep because it's not a wake-up reason. That's the only problem. You know, so
It's a bit of an oversight on their
Yeah.
behalf.
Yeah, damn.
yeah.
I was going to say that's a winning idea already. I was just thinking about it.
If you can find something with an interrupt, like if, for example, a lot of the tilt sensors, you can program them with interrupts. So in other words, you can basically say, just tilt it that much and then give an interrupt. And then that's essentially like the same thing as a Gpio or essentially a button press. So, you know, that's essentially also quite workable. All right, cool. So that is light sleep with also button press. All right, now we get into the deeper stuff. Okay, so I'm going to comment this guy out.
So everything's got to start from scratch with this one.
Yeah, but you'll see that it is not as bad as that sounds
State variable.
because it does have state variables.
Unless you get a lot of mail, right? Like you, if you're in a,
It's the same power draw with the buttons as well.
like most mail, what, 2 maybe 3 a day would be your worst.
Draw with the buttons as well.
Same
so
draw?
button plus timer.
Yeah.
The exact same amount of power you use. Just the timer.
Yeah, pretty much. It depends on how you set it up. You know, if you wire it badly, then the button itself can leak power. You know, generally with a button you need something called a pull-up, which is something else I'm going to talk about now. You either need a resistor that's basically going to the power rail, and the button underneath it. Okay, and then essentially your chip needs to know that it's essentially high, or essentially if it's pressed that it's gone low. I need a whiteboard to show you this. Well,
So
let me
it's
just.
basically, but what it means is the voltage sits at the level of the power.
Yeah.
And the GPIO registers when it's pulled to ground. So it registers when the voltage drops to 0. Rather than the other way around, it sits at 0 and waits till it go high, it goes to 5 volts. So as a pull down goes to 0, pull up. You use a pull up the resistor, hold at 5 volts, pull down resistor holds it at ground.
I'll just draw a very quick picture for you, Sam, so that you can see how that actually looks.
It's just so you get a reliable value to what it's looking for. Like
So-
if you don't, you can like float.
This is gonna. Hang on a second. I got my fancy, cool little thing over here. Let's see if this works. All right. So let's say, for example, this is your chip over here, and you've got this pin over here.
Well, from out, like,
Yeah, I know. This is pretty good. So you've got your switch over here, right, which is essentially effectively an open circuit. Okay. Right now.
Getting uninterested, I just don't understand it.
Oh, that's fine. All right, so this is your switch over here, okay, and of course when you basically press the switch, that closes over there, okay. All right. Now, there's two ways that you can wire this thing up, okay. You can, let's go higher over here. You can have your power line over here. So this is your power line, okay. So this is plus, let's say for example, 3.3 volts, okay. And then what you do is you basically have a resistor over here, like that. Okay, and you have this line over here pointing to that over there. So that's what's known as pull up. Okay, so if you have a look at what the electricity is doing, right, it's essentially powering this thing up at a high voltage. So now you have 3.3 volts at this point over here. Okay, and what happens when I basically close that voltage, right, is now this then goes to ground. So yes, the current runs over the resistor, but because this thing is closer to ground, this thing now goes to 0 volts. So this is essentially a pull-up resistor. You get the other side of things, which is essentially a pull-down resistor, which is the other way around. Let me just, where's the eraser? I'll just draw it over here. So the other way is essentially, you've got your switch again. But this time what you do is you basically have the resistor on the other end, and that goes to your chip over here. Now this is at 0 volts. But this is on power, okay? So when I close it, now all of a sudden this goes from 0 to 3.3 volts. But the problem is, right, that as I'm closing this, notice that current is still flowing through there. And this could essentially leak quite a bit of current if that's a bad value. That could be a short circuit if it's like very close to 0. Right, so you can actually cause damage to your power rail or your voltage regulator if essentially you don't have a high enough voltage or a high enough resistor there. And in worst case scenarios, and in best case scenarios, if this is very low, then of course it's going to leak a lot of current. It's going to throw away a lot of power. So you want something that's the right amount, because if this is too high, then effectively it's the same thing as having an open circuit, then it doesn't work at all either. Okay. So these are called pull-up and pull-down resistors. Okay. Now you'll notice that I've got some circuits over here. I'll show you this over here.
Just because picking batteries.
Okay.
Your laptop batteries getting too low.
Sorry?
Picking batteries, your laptop batteries getting too low.
Yeah, it is. You're right.
Died.
Yeah. Which is surprising because I've actually got the. Let's continue. Are you guys cool with this? Is it interesting?
Yeah.
Okay, good.
I'm learning a lot. I have very little hardware experience, so it's great.
Okay, cool. I'm glad to hear it. All right, let's talk about deep sleep. Okay, so deep sleep, right, is going to essentially restart my chip. Okay, right? Now, do you remember I was talking about this thing called RTC? And we talked about this thing called slow memory. This over here, right, is how I can actually put variables into slow memory. I use this macro over here, RTC data attribute. And if I do that, then I can put something inside of slow memory. And then it does not get wiped out when the chip resets after deep sleep.
Cool.
Okay. So
Probably wouldn't need to store much either.
no, you wouldn't probably. Just a couple of status variables, I guess. Okay, so it depends on your thing, but
Vague recollection, it's the 22 bytes.
I don't actually know.
Something like that. Or the
It's not
RTC,
huge.
the generic RTC Arduino boards you get,
Yeah.
they claim something like about 22 bytes you can store in them.
Just a couple of registers or something.
Yeah. Instead of,
I don't actually know what
which
it
is
is.
quite a few if you need to store just
Like a temperature or something, or
a
perfect.
couple of
Yeah.
Well, we'll have a look. I think it might be more than that for this. I suspect, because I'll show you something a bit later. Okay. But, okay, so over here you can see what's going on here. Right, we run this thing called ESP sleep enabled timer. And again, I'm basically sleeping for 5 seconds. So this is ESP sleep enabled timer wake up. This is deep sleep. Okay, this is how I do deep sleep. All right. Then I say ESP timer start. Now watch what I'm doing here. I'm basically just incrementing this every single time. You'll notice that the chip actually resets. So 5, 4, 3, 2, 1, and it stores the count. It remembers what that count is.
Cool.
Okay.
Just interesting when you're going. I just want to in my head, I'm sort of timing how long it takes for it to restart from DC. It's only about a second.
It's less than a second.
Less than a second?
Much less than a second. You know, also, printing out to the serial monitor is slow.
Maybe half a second.
It's probably, I haven't ever really timed it, but it's quick.
Yeah.
Yeah. And what you probably find that it's actually running, but it's just catching up, trying to basically flush that serial buffer.
That's true. Yeah, that's true. That's probably the slowest part.
Yeah. Because printing is slow.
Instability time, like when it wakes up from deep sleep and goes back to the full power usage, is it
because
worth actually like delaying a little bit to ensure that everything becomes stable again?
I don't think so. I've never really. It's pretty stable. We were putting the tracker to the one of the units that we did, right. We were putting that to sleep and then waking it up.
And then instantly doing
it was
work
instant.
straight
It was no problem.
So your power usage goes straight up.
Yes.
You're not concerned that the voltage is going to fluctuate or anything.
No. I mean, I suppose that could happen if you've got a lot of power draw coming off the regulator, and you don't have a large enough capacitor to handle that power draw. You could potentially,
peripherals running, possibly LEDs.
Yeah, you'd have to basically be powering up a lot of things. If you went on the Wi-Fi and powered up everything, you could potentially maybe drain the voltage down so that it dipped. You'd have to worry. Yeah, but if you have a look at all these things, they've got big capacitors on the power outputs, and then it's not a problem, you know. So yeah, so that's how we basically do deep sleep with a timer. So if we think about it from our letterbox perspective, you could basically sleep this for, let's say, for example, 6 hours, switch it on, check a sensor to see if there was something sitting on top of switch, or if essentially something was obstructing a light, or something was,
I'm just going to throw a scenario
at you and say, like, this is how I envisage it working. But just to sort of keep this example in mind, because I'm just sort of thinking this in the context of that, is that I would love to wake up, tell you there's a letter there,
yeah,
but also tell you what how much what the battery voltage is, so you know how much life you've got left.
Yeah.
So it's basically saying, yeah, saw a letter. Oh, by the way, your battery's got another 6 months to go. You know.
And you know how to do that because we've done that before. You basically just have a voltage divider.
Yep.
But you've got to make sure that you've got high enough values so that you don't drain your battery.
That's right. So you got to get your values right. Otherwise,
yeah,
you're going to sit there.
So just for your so if you got just go back here.
Okay.
Back to the whiteboard. Yeah, that's right. Yeah, what we did is you basically drain a battery and you get all the values out,
Yes.
and then essentially you mark that over time, and then you essentially you plot that like that.
Yeah,
You know?
it's basically like a spreadsheet. Yeah.
So just for your benefit, Sam, if you basically got a high voltage rail or voltage rail, let's say 3.3 volts over here, okay, and you've got essentially 2 resistors over here, okay. Well, this is called a voltage divider. If these are the same value, you're going to get exactly half the voltage over there. Okay, so so if this was, let's say, for example, 5 volts, then you'd get 2.5 volts over there. Okay, and essentially, so if this particular voltage level over here was moving up and down, okay, then obviously this level over here is moving up and down. So if we, let's say, for example, had let's say, for example, we've got a regulator over here, okay, and this was a solid 3.3 volt line, okay, so that never changed. Let me get my pen. So this is a regulator. That's this little sort of chippy over here that I was showing you earlier on my board. That gives you a solid 3.3 volt line. That never ever varies, okay. But you don't want to actually have your regulator over there. So where is my eraser? There it is. Okay, so that's your that's essentially powering your chip, all right. So this over here powers your chip over here. Okay, here's your battery over here. This is your battery, and that basically powers the regulator. But then what you do is you also, all right, out of the other side of the battery, you basically have this voltage divider. Okay, and let's say, for example, that's, let's say, 5 volts coming out of there. Okay, and then they got 2.5 volts over here. Okay, and that goes into your chip. That's 2.5 volts. It's less than 3.3, so it's safe. Then your chip can essentially
Off the ADC.
your chip can now measure this voltage, and as essentially this battery gets flat, this goes to 4 volts. You see this over here, because it's regulated, doesn't change. That's 3.3 volts. But this over here is going to go 2.5, 2.3, 2.1, 2. Whatever. And then essentially you can tell how much more power you have in your battery. That's essentially how they measure the battery.
Cool. Okay.
Okay.
So what sort of values would you have for those resistors?
Yeah, it's important. They've got to be pretty high values.
They've got to be
Mega.
high. Huh?
Mega.
I'd say hundreds of K.
10K? No?
Maybe 100K each.
Depends on your leakage current
Yeah.
and ports.
It
Yeah.
does.
I'm trying to think what
I can't remember. I think
what
we
values
used. I think we used 200K.
Yeah. God, I've got it written down.
It's not going to be a lot because if you basically work it out in terms of, let's say for example, you've got a 5 volt supply of your battery. Like all these lithium-ion batteries, those little polymer packs, they're what 4.3 volts, and then they basically start tapering off 4.2, and then they go 4.1, 4.3, blah blah blah.
You can push them high, but you should.
So if you basically, let's say for example, got 4.2, let's just work this out. So if you got 4.2 volts, okay, and we've got, let's say for example, 200,000
You've got a range of 4.2 to 3 typically.
yeah,
before you
but I mean just in terms of voltage
2.8,
leakage.
4.3.
So if you've got a voltage divider with two, let's say 200, 100k ohms, so that's 200, 1, 2, 3, you're going to get a current leakage of 21 microamps, which is not too bad.
If you were
There's definitely a penalty, yeah.
if you were really worried about it, you could switch out, like put a FET to
Yeah.
ground and switch it out and just look at it when you want it.
You probably find that 21, look, if you raise it to 500k, but obviously the more you do that, the less reliable your voltage divider is going to be. Yeah. So that's your price.
Around like the ADC, which is running out of resolution to
Yeah,
because
yeah.
they're reading your value.
Well, I just think I'm just trying to think what comes down. It's like, yeah, if you're blocking too much current, the ADC is just not going to insufficient.
Yeah.
It's just not enough to actually drive it.
Yeah.
You get to a point where it's sort of flaky on the edge, but I don't know what that point is.
I don't know either. But I think we were using two 100Ks, and that's essentially the penalty we were paying, 21 microamps, which is not
To be honest, the best
not
way
too
to
bad.
answer these questions is actually just play with some resistors and see what happens. So half the time, if you really want, super resolution, or do you want to just say, oh, look, I've got to change the battery, I've got about a week before I need to change it.
Okay, so that's essentially deep sleep. You can see it's very easy to put something in deep sleep and remember something, okay, and wake it up after a particular amount of time. All right, let's go into the next one. Right, so now we get into EXT. All right, external. So let's go back to here because I think I basically made a note of this. Yes. So there's two different types of external wake-ups. EXT0, external wake up 0, and EXT1. Okay, they both work on the RTC. There's just two options that you've got. Okay, so the nice thing is, remember we talked about the pull-up resistors, right? RTC will enable you to have pull-up resistors. So in deep sleep, you don't have to actually have extra circuitry.
You can tell it.
You can say,
You can
I
tell
want
it activate your built-in.
activate your built-in, pull-up and pull-down resistors. Okay.
Yeah.
Yeah. So with EXT0, you get internal pull-down, pull-up or pull-down resistors that can be used. So it's essentially free for all. Okay. So that's one option. The other option is EXT1, right? So internal pull-up or pull-down resistors can be used, but only if you basically enable part of the RTC. Okay, which is the RTC peripheral stuff. Okay, so you'll see later on, right, that when you'll see basically what this basically is talking about is something that will make a lot more sense in just a moment when I talk about the levels of degrees of deep sleep. And you can actually fine-tune how deep a sleep you want to go. You can turn things on and off. Obviously, the peripherals is one of the things that you can turn on or off, such as the UPC, the ultra-low power, I2C, SPI, ADC, and all that sort of stuff, right, is something you can turn on or off while it's sleeping. Okay, and if you keep it on, you can basically also have pull-up resistors or pull-down resistors.
Do you also have control over the oscillator that you can use?
Yes, you do. There's two oscillators that they have, and I'll show that to you afterwards. Okay, we'll go into deeper detail with that. Yeah. Okay. So you've got two options over here. You can wake up if any selected pins is high, Okay, so this is essentially the flag that you use. So you can have multiple pins, and you can say any one of those must go high in order for me to wake up, or you can say all of those pins must go low. So that gives you essentially an AND gate, where you can say I want that and that and that to happen before I basically go out of deep sleep. Okay. All right, so let's have a look at an example of that. So I'll go ahead and flash this. So this is deep sleep with EXT0, all right, and this is really straightforward and very simple. Okay, so
When you said all pins, that was all pins that
that you specify.
you specified.
Yes.
So not just the whole. Everything.
No. No, that's right. So here we basically are specifying one pin over here, Gpio25, okay? Okay, and we basically say RTC Gpio D in it, okay? Then essentially we're saying that we don't want to use it for general purpose. We would want to use it for RTC, okay? And we would need to undo this if we wanted to basically use it for GPIO again. We would basically reset it. Okay, so there's a counterpart to this guy over here. Okay. It does an internal mux. Yeah, that's right. Exactly right. Okay. So then what we can do over here is we can say pull up enabled and pull down disabled. So, you know, so obviously if we have both enabled, we've got a voltage divider. I don't know why you would want that in there, but
That would be handy.
you can't read off the middle, so I don't know if you can actually. You might be able to.
No, you just get a nail.
Yeah. So, so you can basically get your pull up and pull down resistors over there. So you'll notice I've got these two buttons over here. No pull up or pull down external resistor. It all works. Okay. And then essentially you can say ESP sleep enable with EXT wake up, and then essentially the button. And then this last parameter over here is the level. So you can decide whether you want to wake up either on a high or a low. Okay. So let's go ahead. So you can see it's going to sleep. All right. And I can go ahead and press this button, and you can see it's woken up once, woken up twice, and so on and so forth. So essentially it's also keeping the RTC memory in there. Okay? So very straightforward. All right, let's have a look at the next one. All right, this one is external 0. Okay, or external 1, sorry. So let's have a look at EXT1. I'll show you how that works. So in our terms of our letterbox, I'm not quite sure how we would want to basically do that. Maybe we want to say that, you know, like we need somebody to open it up, and we need a wait or something like that. We need, you know, we need two switches of some sort.
Someone opened it and shoved a newspaper in and left it hanging out, and
Yeah.
it all stayed up.
Yeah.
Or you could say, lift it, I'm now listening, put a load sensor on it, go, oh, it's a very heavy piece of mail. That's input. Could be input. So my batteries are used.
So over here you can see I'm specifying two pins, okay, Gpio 25 and 26, okay, and I'm deinitializing. Now I basically set up ESP sleep PD config, okay. So what I'm doing over here is I'm basically saying, and we'll look at this again just now, this is a hint as to how I can control the power domain of the RTC. That's what that stands for, the power domain of the RTC. So I'm saying I want to enable the peripherals.
So power them up, basically.
Yeah, I want to power up the peripherals. And this allows me to use the pull up and pull down resistors. So I'm basically enabling and disabling the pull up and pull down resistors on both of those pins, on 25 and 26. Okay? Then I basically create a mask and basically just pushing both of the button 1 and button 2 into this mask. Okay? Because that's essentially what ESP sleep enable XT wakes. It wants to know how many buttons, or essentially which buttons do I want to basically wake up on. So this is an OR shift of all of those buttons that I care about that are going to wake up. Okay, so I care about either 1 or 2. Now over here I can basically say ESP external wake up all low, and the other option is any high. So those are the two options that I've got. Okay, so we'll say all low. All right, and let's go ahead and just make sure that I've got that one running. So the way that we've got it configured at this point in time If I press one button, nothing happens. If I press the other button, nothing happens. If I press both buttons, then it wakes up. Okay. So pretty straightforward. Okay. All right. Now we talk about. Now let's go back to the slides.
So you could launch it in like one key here and one key there.
That's right. Yes, that's right. Then it wakes up. Yeah, that's right.
Battery powered nickel, no problem.
So now it comes to your question that you had, right? What is it that I can control, and can I control the oscillator? All right, so these are the various different things that you can control. So we use this, as we saw just now, this ESP sleep power domain config, and these are the various different power domain configurations that we can have. And then we've got the options. We can either switch it on or off. So essentially we talked about the peripherals that allows me things like Gpio enables me for, pull up, pull down resistors and the ULP, I2C and all that stuff, right? The slow memory, all right, we can basically turn that off. We've kept it on right now, and we'll have a look at an example of switching that off in just a moment. The fast memory, that's essentially the fast memory of the chip. Okay. The external oscillator, all right, the internal oscillator.
Just for my benefit, what's an oscillator?
Oh, so okay, so an oscillator is essentially something which is basically going high, low, high. It's giving you a clock signal, and it's oscillating. And every single microcontroller or CPU out there on the planet needs that to know how to basically count or basically execute an instruction set. But I'll show you this in the meantime. Check this out. This is interesting. So over here, I've got the next one that I want to run. Okay, and it looks very similar to the other stuff we've done, but this time what you can see is that I'm actually turning everything off. All right. And the only thing I'm not turning off is this RTC slow memory. Okay. Now this is known as hibernation. Okay, so this is going to give you a very, very deep sleep, and that's going to basically draw incredibly small amounts of current. Okay. Still, it works with 5 seconds. But what we'll do in just a moment is we'll run a bit of experiment. So you'll notice that it still works. So waking up 0.
That's your counter variable. Still there.
Wake up 1, yes. So if we basically get rid of this one, we say we don't want slow memory anymore. Let's see what happens then.
Counter variable doesn't count.
We'll see. Huh? Well, yeah, look, it does what you typically would expect in C. Okay, and you'll see what I mean by that in just a moment. In other words,
Some crazy number, that's right.
you get first one looks okay, and then all of a sudden you get total rubbish. Which is just like, okay, I'm just, randomly set memory, whatever, that's just,
Oh, so you are reading the value back. It just happens to have
crap in
noise
it. Yeah.
Okay.
Yeah.
Random number generator, what are you talking about?
Well, it's not that random. It actually seems to just, change now and again, but who knows why or how.
Pseudo-random.
Yeah. So that's essentially deep sleep. So now you know how to basically take something that is deep sleeping, and depending on what you want to do with your letterbox, you could basically turn that down really, really low. So let's say we come back to our thing over here. Okay. At the moment, we said that we are basically consuming. What was the milliamp hours? Where was it? Okay, duration code execution, 5 seconds, sleep time, hardware consumption during code execution, consumption during deep sleep mode. We said 150 milliamps. Okay. If we basically go back here, we could see that with deep sleep, we can get up to 2.5 microamps. Okay, if we turned everything off. Okay, so let's go 2.5 microamps. And now all of a sudden we're up for
2.5. Oh, that is micro.
Yeah, now all of a sudden we're up for 2,276 days.
Cool.
Okay. So
that's
Meals is paying breakfast.
yeah, totally.
that's right. Your letterbox will fall over before it runs out. That's
So
right.
you wouldn't need a rechargeable battery.
No. No.
No, you just replace every time you paint your letterbox. I think it's probably that.
Yeah. How much is that, by the way? 2,270.
That's
That's
still
a
6 hours as well, right?
yeah. That's with every 6 hours. Yeah, divided
Yeah,
by
and it's probably a good,
365.
probably a good reference.
So
for
yeah,
if you're
that's
waking up with
six
a,
years. So Yeah.
Yeah, if you're waking that up with a reed switch,
Which you'd probably get 3 deliveries a day from a post office, maybe some junk mail. So it's probably similar. In fact, even less than that, probably. So you end up...
Holidays, nothing.
So you basically set and forget.
Right. So now you know how to take it from one day up to several years.
so that says to me that if you're doing
Something simple like a reed switch, triggered circuit.
Yeah.
You'd be crazy to have any external circuitry, just let the chip do everything.
That's right. And literally, you go online, you basically spend a couple of seconds just sending an email. I've got the code to basically be able to, using SendGrid, to just send an email,
yeah.
saying, yeah, you got mail, that's it,
You have
done.
electronic mail?
Yeah, that's right. You got electronic mail that's telling you got real mail. Okay. Now,
It's called an A to B converter.
there is one thing I just wanted to mention before I forget. Let's just go to this thing. So this guy over here, DF Robot ESP32. If you want to basically, if you don't want to create your own board and your own regulator, this fire beetle over here is renowned for being one of the most power efficient. I can't remember the exact specs on this thing, but this thing is, you can see if you have a look at it, right, it's actually got a buck converter on it. It doesn't have a regulator on it. I can't remember what it was, honestly. I'd have to re-look it up again. But it was, like, you put it into deep sleep, it's pretty damn close to what you actually expect.
And it's $6, like, why would you build your own board anyway, right?
Oh, these ESP32s, I don't buy them for more than $5. They are crazy cheap, and they are bloody powerful microcontrollers. They're really good. All right, so I had a student, all right, who, because I don't know if you know this, I run a course online for learning ESP32. So I had a student who basically was producing an app. So I had a student who was basically producing a project, and I can't remember. He didn't actually specify what he was doing, right? But he had a really interesting little sort of problem, right? He was basically running something with a trigger, much like we were going to do with our postbox, right? But what he basically wanted to know, right, was how long was I asleep for? Because essentially, normally we either go with sleep with time or we go with sleep with a trigger, okay? So how long was I asleep for? Now, if you have a look at the light sleep stuff that we looked at earlier on, okay, we were basically using something like this, where we said ESP timer get time.
Yeah.
We start and then finish. But remember that we reset the chip, so this is not going to work. That's going to be essentially the same value every single time we reset the chip, okay? So I answered his question, and this is essentially how you do it, and I'll basically show this to you, because this is actually really interesting. So the C library, the standard C library, all right, offers us this particular function called get time of day, okay? This get time of day, right, obviously if I reset the chip, it's going to be defaulted to 1970, sort of, like something like that, okay? Which is okay, all right? Because we can use NTP, standard NTP, to basically go online and basically get the time. And what's beauty about this, right, is the fact that get time of day persists in RTC slow memory. Okay, so what we're basically saying here, right, is that if you've basically configured your circuit, or if you've got it hooked up, right, and you get the time, you can hibernate
And hold it.
and you will not forget your time.
That's really cool.
Okay, so what we have here is, I don't actually display the actual time itself. There are functions that will allow you to do that. What I've got is essentially the milliseconds since 1970, or 1970 being today, because obviously I've just powered the thing on. Okay, but what's really interesting, right, is if I basically go ahead and press this button, right, you can basically see that it's been asleep since I repressed it for 84 seconds, right, and the time that it's been sleeping is for 84 seconds. Now if I press it again, you'll notice, right, that it went to sleep for 10 seconds, but the actual time since I've actually powered it on was 94 seconds. Okay, so it's persisting the actual time, and that is something I can actually convert to a daytime as well. So the last thing as an additional, but I think that's everything I wanted to talk about. Oh yeah, I also wanted to talk about these guys. Okay, so regulators, right, for fantastic for basically if you got something permanently plugged in. 30 cents a piece, very cheap, right? Very easy to configure. Okay, versus a buck converter.
Oh, there is another advantage of regulator.
Yeah.
It stops frost building up inside your letterbox.
Because it's hot.
Yeah,
That's right. It dispenses a lot of heat. Boost converters, right? Whereas this is 30. Yes, that's right. That's right. Whereas this thing is
Never
like
win.
30, 40 cents. This thing is going to basically cost you $2.5 or something like that. All right, so significantly more expensive. But one of the biggest problems that we've run into as a company with buck regulators is the fact that the minute you plug in your cable to charge your circuit, because it's got a massive oscillator on there, and you can see essentially it's got a big coil on there, it acts like an antenna and it fails CFC certification. So you got to come up with choice. So it's a much more complex solution, specifically if you're trying to if you're doing it for yourself, then who cares? But if you're actually trying to produce a product that's going to apply certificates whenever,
So it
you got to be
generates
careful.
radio noise.
Yes.
Yeah, so
Can
because they're basically MOSFETs, aren't they, on it?
Yeah. So there's essentially
And because they're high-speed switching, essentially, the high-speed switching creates resonance waves, and if it's propagated along the wire
yeah. So in this
or any
slide
part of the
deck,
circuit,
Okay, turns into a transmitter.
and if it's in the 100 megahertz range or whatever, it's like aircraft, etc.
So in the slide deck, which will be available on the meetup, right, you've got these resources over here. This is basically giving you just basically show you, this is a boost converter calculator. So this is basically showing you if you basically want to get a 1.5 volt battery, what is your cost in terms of your capacity? So you can get a boost converter on AliExpress, they're pretty cheap, okay? But let's say, for example, you want to basically go for 20, 1, 2, 3, 4, 5, 6, and your minimum voltage is, let's say, for example, 1.2, your maximum input voltage is, let's say, 1.5. So that's essentially a pen-like battery or AA. Your minimum output voltage is 3.2, and the maximum output voltage is 3.6. Okay. And your current, let's say, for example, you're going to need at least 150 milliamps to basically worry about power, like the radio spikes and stuff like that. Maximum, well, let's keep it that. So you can see over here that we're basically spending almost an amp. Look at that. 700 milliamps. That's ridiculous.
Well,
Did you put the right?
Couldn't have been.
Scroll up a bit again.
The
That hertz.
20
value.
kilohertz.
I think you put too many.
20 megahertz?
Yeah,
it's
it's
too many
too
zeros.
Too many, I think.
Okay,
It's in hertz.
20, 1, 2, 3. Yeah, 20. Let's go for that.
That's 20 kilohertz.
Yeah, 20 kilohertz.
It's quite a low frequency.
Still quite high.
Yeah.
702 milliamp. That'll drain your battery in no time at all.
yeah, that's Raspberry
That's
Pi
like-
level, right?
But that's through an inductor as well, so it's
Yeah.
generating magnetic fields.
Yes, but it is
That
possible to
current.
do it. So maybe that's right. Maybe I've done something wrong. But
No, but
you get the idea.
but you're talking about your supply voltage is 1.5. You change that to 3.6. See what happens.
Yeah, then it's going to drop off a lot. But
Yeah.
so.
Because you put a lithium on there.
Yeah, but this is a boost. This is for boost converters.
Oh yeah, sorry. Yeah,
So
yeah.
if I'm going to go it down, I'm going to be a buck. The other thing is with a regulator, also you got a voltage, 1 volt at least voltage drop across it. So you've always got, if you've got a 3.3, you've always got to at least be a 4.4 or something like that. Okay, which means as your battery goes below 3.7, you lose it. So something else to keep in mind. All right, so then over here I've got
Do voltage
essentially
regulators stop functioning pretty much straight away, or they glitch?
they glitch.
Okay, that's
Yeah,
not good.
especially if you don't have a heatsink on them.
Okay.
Yeah, then they really glitch. So if they're consuming a lot of power, then yeah, they switch. They basically overheat and they switch off and they switch on and they switch off and they switch on. So over here I've got a buck converter. These are some YouTube channels that basically give you some really nice 3D. After you basically watch all the stupid freaking adverts.
This is a wonderful community. Vibrant, caring,
Don't
diverse.
care. Go away.
To step down AC voltage, we use a transformer, but how do you step down DC voltage? We use a buck converter. What is a buck converter? A buck converter is a transformer that converts AC voltage into DC voltage. We use a buck converter. In this video, we will be exploring the design process and working of a buck converter, which is used to lower the DC voltage efficiently.
All through how those work, so you can have a look at those. So there's a buck converter, there's a boost converter, okay, and also buck versus regulator. It gives you some sort of idea as to what's going on there, okay.
You can get buck boost as well.
You can get a buck boost as well, which is quite nice. Okay, that's especially for sort of batteries that could drop below the threshold.